Introducing PowerChain, a metadata system for lithium-ion battery life cycles. So in this talk, I'm going to discuss what lithium-ion is and some of the current applications for it in the market. And we're also going to talk about life cycles of batteries, which include recycling and waste. In particular, I'm going to zoom in on the material flows analysis of lithium and cobalt, the way in which these materials are transformed at different stages of the life cycle are opportunities for injecting metadata collection into the life cycle of the battery. And then finally, I'm going to discuss the concept for a database for storing this metadata and adding to it and then reading from that database. So we begin with lithium. It's the third element. It is an alkali metal. It's the lightest metal and actually the lightest solid element, but it is highly reactive and flammable, which means its occurrence is a kind of strange in nature. It really only shows up in these brine pits, and then there are all these types of rock in the earth crust where lithium can be extracted from the earth and then refined. In the 1970s, it was discovered that lithium is useful in energy storage as an alternative to alkaline cell type batteries, and lithium is a preferable alternative because of its high energy density. So there are several types of lithium batteries. There are single-use batteries that are perfectly analogous to their alkaline cell counterparts. The button cell batteries, the CR2032s that are everywhere, are lithium type single-use batteries. But there's another type called lithium-ion and the closely related lithium polymer that are used in rechargeable applications. Some of the most common ones that you'll encounter are portable electronic devices like phones, computers, and e-cigarettes. Also power tools, but really importantly, electric vehicles and aerospace applications like drones. So I'm going to look at a specific type of battery, a specific size, this 18650 size battery. It is a cylinder form factor, and just because it works like all electrical devices, it can be used as a component in combination with other identical batteries to create much larger battery cells. And that's exactly what's done in this case, the 2014 Tesla Model S. That model car has 85 kilowatt hours of lithium-ion battery storage inside it, and that battery is actually composed of more than 7,000 smaller 18650 sized batteries. But these same batteries are also used in other applications like laptops, where you might just combine a couple of these 18650s into a bigger component that then, it's a module that you plug into a laptop and it provides a battery for that. Or even actually just as a straight up 18650 inside a flashlight or something like that. So the reason I am looking in particular at electric vehicles and the batteries that go into electric vehicles is because the market size for electric vehicles is predicted to just continue growing. All these lines go up. And in order to create 10 kilowatt hours of battery capacity, that requires a kilogram of lithium to be extracted and refined. So it comes out of the ground and it ends up back in the ground when things go wrong. When things go right, when recycling intercepts these batteries before they hit the waste pile, then we can avoid pollution that comes from lithium batteries. And it's worth trying to avoid because there are a number of ways that the environment is impacted by the disposal instead of recycling of lithium batteries. So a recent study looked at environmental impact data collected 10 years ago in 2005, but they found more than 1,000 tons of heavy metals are leaching into landfills and potentially then reaching water sources. And lithium itself is toxic to humans and to plant life. As an element, it is not essential for life, so there's not really a good reason to have lithium in your food supply. There are several reasons why you want to intercept this lithium before it ends up back in the environment. When you actually look at the way electric vehicles are disposed of in the sort of the waste process at the end of the electric vehicle life. There are a couple of scenarios depending on how the car is decomposed into its chassis and the battery component, because the car could reach end of life, but the battery component may not be at end of life. It could actually have years left of good service. So that's what occurs where this one arrow is pointing. At the end of the lifespan of the car, the EV, the electric vehicle, can be at end of life, EOL. But it could have a non-end-of-life battery. Now, in the case that it's an end-of-life car and an end-of-life battery, then you dispose of both things using the existing approach. But in the case that the battery is still good, that's a point where it would be really useful to have the metadata about those batteries to be able to make a decision about what to do with those batteries. And in particular, that if the batteries are decomposed into their principal components of the individual cells, that metadata stays with the cylindrical battery cell. The metadata is not locked inside the aggregate component, that it can be deaggregated into small individual components, and that each component still has the metadata, the life cycle metadata attached to it. One way of measuring the total energy impact of a car is to look at the thermal units that are expended, and these thermal units include every component in the manufacturing process. So the energy expended for resource extraction, the energy expended for assembly. This is the total energy that goes into moving it. And based on a life cycle analysis for lithium-ion battery production and recycling, the argument is made that just by increasing recycling according to a specific use case, the total energy impact of moving the same distance can be dramatically reduced from 90 BTUs per mile down to something more like 65 BTUs per mile, just by recycling more effectively. And so a system that facilitates recycling, according to this argument, can reduce that total energy impact. So lithium battery recycling, they're designed to extract cobalt, which is on its own rare and precious, lithium, which is just expensive to mine, nickel, which is just expensive to mine. None of these elements is recaptured at an especially high rate. Each of these elements ends up in landfills at a rate higher than we want. And cobalt in particular, because it is rare and precious, it's regarded by several countries as being critical to their national economies because it is used in the production of energy storage devices, these batteries. And the places where we get cobalt on Earth, where it is mined, can potentially be geopolitically conflicted. So this image is the material flow analysis for the life cycle of cobalt. It comes out of the lithosphere. It starts with mining, the point at which cobalt is taken out of the Earth's crust. Then it is refined, which is a slightly lossy process. There are some residues that are created as a result. The refined product, that is to say cobalt, is fabricated and manufactured. So in this case, it's used as part of the cathode of the lithium-ion batteries that we're talking about. Those fabbed batteries are then put into use. They're used in cars, they're used in laptops. And then finally, those batteries are discarded. They become waste. And at the point of waste, that's where recycling occurs ideally, or reuse, or at the end of life of the battery, then disposal. And some of this cobalt can be recovered in the process. However, in the analysis of this life cycle, a significant amount of waste is nevertheless unaccounted for. And a metadata process would mitigate how much of this waste is unaccounted for. So the metadata can be assigned at the point of fabrication, and then all through the point of use to the point of waste, where that metadata is used. So there are a number of regulatory frameworks for recycling. In practice, there can be recycling at the regional, the federal, or the international level. And there are three main models that I've come across so far, including voluntary collection. So in the case of batteries, some industries in some countries voluntarily collect lithium-ion batteries and dispose of them. And this is basically the free market solution. So the industry sometimes opts in and actually just voluntarily collects batteries and recycles them. Another alternative is a government tax that is levied at the time of sale. This is sometimes called an eco-tax, and an example of what it might do is the money is collected by the government. It's assumed that the battery is going to end up in a landfill, and then the money that was collected by way of the eco-tax can specifically mitigate negative environmental impacts, like, say, mercury that is leached out of a type of battery. And another style is a deposit refund scheme. This is where you pay for the battery and you also pay at the time of purchase an extra percentage, and when you then bring the battery back at its end of life to the store where you purchased it, you can get that percentage extra that you paid refunded. This has been tried with another type of battery, nickel cadmium, and at least in the German study that was conducted, they got 10% of the batteries back, which is a whole lot more than zero, and they also had reported low incidences of fraud. But it is still the case that when you're trading something that's presumably now worthless, the end-of-life battery is worth nothing, and you're getting back something, money, then the potential for fraud exists. But apparently in practice, there wasn't a ton of fraud. But it's even if it doesn't occur within a country, then this type of scheme can also be defrauded using import schemes. So no matter what you do, fraud is still an issue for a refund, a deposit refund scheme. The real challenge for these batteries, these 18650 batteries that show up in all sorts of applications, is that there's a projected steady increase in demand for these specific types of batteries for the next 30 years. And at a minimum, there's an opportunity for recycling due to this life cycle mismatch, where sometimes the batteries last longer than the products that they're inside of. And there are other opportunities for recapturing metals before they end up in the waste stream, if only we knew more about the batteries at the time of disposal. Mining, refining, manufacture, sales, and waste are all steps in this life cycle that can occur in different countries. There are demonstrable environmental impacts of lithium pollution, and the tracking information about these batteries over their life cycle. Data is lost simply as a consequence of these batteries passing through a global marketplace, where the country of disposal may well not be the country where the mining occurred. And it might not even be the country where the battery was manufactured or even sold. There are a few goals for this project. The first is the increased reuse of non-end-of-life batteries. The next is the increased recapture of precious and expensive metals, cobalt, lithium, and nickel. The third goal is to reduce the lifetime energy consumption per battery, just generally through the argument that increased recycling can reduce the lifetime energy impact. And whatever this solution is, it needs to work in a global marketplace. It needs to be resistant to a process that is lossy simply due to the fact that the battery, depending on where it is in its life cycle, is likely to be in a different country from where it was in the previous stage in its life cycle. What I'm talking about here is going to be a proof of concept. It's a simulation, when all is said and done, of a system that I'm calling PowerChain, which is a public global database of battery product metadata. Now, this is built on consensus protocol that works kind of like a blockchain. And the basic idea is that cryptographically secure identifiers can be attached to the batteries, and then those identifiers can be used to track the battery in this database without requiring the various institutions that use the database to have to trust one another along the life cycle. So I have a picture here of two 18650 batteries, and you'll notice there's a barcode. This barcode is unique for this particular manufacturer. They put a unique barcode on each battery. That's pretty standard for quality control. If something goes wrong, you can see that battery, and that company can debug the process, but it's a private identifier. Nobody else really can make great use out of this product identifier. It's inside that company's database. If that very same information were globally identifiable instead of restricted to the use by the manufacturer, then that metadata would support a material flow analysis and life cycle analysis, really, of these batteries without data loss or with less data loss. And as a result, there will be new opportunities for recycling interventions. Just because we have more information about the batteries, we're checking in on them at more points in the battery life cycle. Once again, this is what I'm talking about. The arrows point to these three cases where, in the case of the end-of-life electric vehicle with the non-end-of-life battery, that's a situation where you need the battery metadata right there to be able to assess how close to end-of-life the system is. And in the Cobalt material flows analysis, I'm pointing to the state, the moment of manufacture and the moment of disposal, the moment of waste, because those are points where the data can be injected and read. At manufacture, the metadata is assigned. At disposal, the metadata is read. So these are two kind of depictions of in some ways the same thing. It's explaining where the data gets in, and it's explaining where it's used in the life cycle. And this is all it is. There's a scanner. We're just simply talking about what is kind of analogous to assigning a barcode and then at other times reading that barcode. So this is a little bit of what it could look like. There is this global power chain database that exists kind of at the top of this picture. And let's say there are two countries where, again, we're assuming that the battery is probably not manufactured in the country where it's used and the country where it's disposed of. But let's just say that a bunch of these batteries are created in these two countries. More batteries are made in country A than are made in country B. So one model for how this could work is country A can assign identifiers to each of the batteries that are manufactured in that country, and country B assigns its own set of identifiers, and there's more because there are more batteries in that country. And then now all of these batteries are represented in the same database. So we have a person at the very bottom of the picture. The person goes to a store and they purchase the batteries. They use it for the lifetime of the battery. And then the recycling sign represents the point of disposal. And that's the point where the database is then referred back to. And the batteries can be compared to their initial metadata. So a few things are possible at that point. This is one way that a refund system could be instituted in a way that would be more resistant to fraud, simply because the database itself, by being analogous to other blockchain technologies, it inherently resists duplication. The classic problem is double spend. Also solves the double redemption problem of batteries. So they are the same problem. How would this system ever get started up in the first place? Here's one idea, recycling incentive-based system, but this wouldn't have to be the only way. To the extent that a single battery gets associated with a single identifier in this power chain, that creates a mapping between a token and a battery. You could imagine then that the sale price of the token is the redemption value for the battery, that they become exactly equivalent. And one way that could be instituted in the first place would be by countries and investors engaging in a marketplace where these tokens are traded. And now mind, that the token itself exists because there's actually a physical battery in existence. So one way that you could bootstrap this system economically would be to look to other blockchain applications and to draw an analogy to carbon offsets. So an idea here could be that if a country manufactures 20 million batteries, then that country purchases 20 million tokens, and then those tokens are resold to the manufacturer. And in the same way that carbon offsets create some kind of economic equivalence with their energy consequences, these batteries as well have an equivalence between the value that they represent and their energy dynamics. So in the same way that carbon emissions can be offset economically and traded between countries, you could imagine a country doing something kind of like a bond purchase and then reselling this inherent energy capacity on a global marketplace. And in that process, because these tokens are fungible, they become tradable energy assets. They have value. So the infrastructure for this really just consists of a public browser for the power chain, blockchain, and wallet applications that are used to read information about batteries, update information about batteries, and potentially redeem batteries. That doesn't exist yet. That's just the plan. But that's where we're headed. And what that's actually going to take the form of for my next deadline, my next goal, is to simply run a simulation of this whole system without actually developing any of the technology, to simply simulate a human population that uses these batteries and then compares the current situation where there is no life cycle battery tracking and compare that to a model of a world where this battery metadata is available, and I will make a comparison of the environmental impacts. So wrapping it all up, demand for lithium-ion batteries is increasing for a ton of reasons. And there are a couple of key points for what's called a metadata intervention along the battery product life cycle. So the challenge here is to increase the reuse of good batteries that are not at end of life, to increase the recapture of precious metals and expensive metals, and to reduce environmental pollution at the point of waste. And the solution for all of this, I think, is just a robust life cycle metadata system for battery products. All right, thank you very much.